All right. Hello, everybody. Welcome back to our Wednesday High Energy Talks. Thank you for joining us. Thank you to both of our speakers for agreeing to speak. So we will get started. As a reminder, we take questions at the end, but if you have a question as the talk is going on, feel free to put it in the chat and we'll read it out at the end as well. So anyways, without further ado, our first speaker today is Cory Zhao. He is currently a PhD candidate at the University of Alberta, working with Dr. Craig Heinke. His research focuses on multi-wavelength studies of X-ray sources in galactic globular clusters to discover and investigate potential accreting compact objects. So Cory, please go ahead.
All right, thanks for the introduction. Thank you for the invitation to the seminar. My name is Cory. So today I'm going to present on globular cluster X-ray sources, specifically on identification of the X-ray sources in globular clusters. So here on the cover slide, I have two images. On the right is a Chandra color-coded image of one of my favorite globular cluster, NGC 6397. And on the left is a nice Hubble image of the same globular cluster, zoomed in the core, so you can get a nice image view of the optical sources in the cluster. And also here on the right, you have the individual X-ray sources. So my research is to identify each individual X-ray sources in different globular clusters using multi-wavelength observations. So just as a simple recap of history, studies of globular cluster X-ray sources has a long and fruitful history and can be dated back to early 70s with the launch of early mission like Huru and OS07s that discovered X-ray sources, mostly bright X-ray sources in globular clusters. And these are attributed to mostly low mass X-ray binary systems containing neutron stars in these binaries, and because they show type 1 X-ray bursts. That's a typical signature of neutron star low mass X-ray binaries. And later they were found that globular cluster X-ray sources are overabundant compared to the whole galaxy. That means if you do a rough calculation, you know the per unit mass number of X-ray sources in globular cluster is roughly 2 orders of magnitude if you do the calculation for all the X-ray sources in the whole galaxy. So this was soon attributed to closed binaries formed or created by dynamical encounters and processes in globular cluster, partially facilitated by the very unique environment in globular cluster. You know, the stellar density in the core of the globular cluster could be very high, so orders of magnitude higher than anywhere else in the galaxies. So that facilitated many close encounters that can create these close binary that are also active X-ray emitters. So later with the Einstein and Rosette missions, many faint X-ray sources was also discovered in the direction of globular clusters that are typically below 10 to the 34 per second. So here on the right, I have a Rosette HRI image showing the globular cluster NGC 6440. So you can see the so the dashed red circle here represents the size of the core, and the green solid circle is the half-light or half-mass radius of the cluster. And you see there's some X-ray emission from the core of the cluster, but it's not well resolved due to the limited angular resolution and sensitivity of Rosette. So later with the Chandra, with a superior angular resolution and sensitivity of Chandra, a plethora of more globular cluster X-ray sources, especially the fainter X-ray sources, was reviewed and discovered in globular clusters. So here's the same globular cluster but viewed with Chandra. So you see, this nicely demonstrates this idea of overabundance of X-ray sources in the core of the globular cluster. Actually, 6440 is one of the densest globular cluster that have a very concentrated distribution of X-ray sources, and some of the sources are very interesting to study. I think two or three of them are low mass X-ray binary, and there are several bright CVs and some pulsars inside. So it's a pretty interesting cluster study. So for the faint sources, it was also suggested that some of the faint sources are also dynamically formed, and some of the faint sources are primordially evolved of the primordial binary systems in the globular clusters. So here I have an animation showing a binary single exchange interaction. So you have a compact object in cyan and a normal star, a pair of normal star in the binary. So you see they can go through this encounter for several times, and at last, one of the component of the binary got enough recoil, got kicked out of the binary and forming an even tighter binary as a result. So the tighter binary could be a typical low mass X-ray binary with mass transfer, so it can be observable in the X-ray. So there of the faint source population in globular cluster, there could be multiple source classes. Of all the faint sources, there are 4 major source classes you can expect. So you can classify the faint sources and also the bright sources into these 4 categories. So the most typical and probably the most well-studied source class are known as the low mass X-ray binaries, as I mentioned. So these are accreting neutron star or accreting black holes in orbit with low mass companions. And they're usually, for the neutron star system, they're usually classified into transient systems and persistent systems, with transient systems stays at the quiescent level most of the time and went on the uppers for some occasionally, whereas the persistent system stays at the relatively higher luminosity, above 10 to 36 ergs per second. So it's creating at a continuous level, continuously high level. And then we have the millisecond pulsars, which are closely related to the low mass X-ray binary population, because millisecond pulsars are thought to be the descendant of low mass X-ray binary through accretion onto the neutron star. The accreted matter carries angular momentum that can spin up the neutron star to millisecond, to rotate at millisecond time scale. So here's a nice animation, nice animation that demonstrates this idea of millisecond pulsar in a binary. So millisecond pulsars in globular cluster can be either in binary system or observed to be isolated in some cases. So for the binary millisecond pulsars, they're usually in a very close orbit, so that indicates very strong interaction between the neutron star itself and the companion star. As you can see, the companion star is continuously blown away by emission and pulsar winds and pulsar emission from the neutron star. So that can generate very strong hard X-ray emission sometimes. And for the isolated system, you see more of the thermal emission from the hot neutron star surface. And next we have cataclysmic variable, or CVs. So cataclysmic variables are accreting white dwarfs in orbit with low mass companions. And actually, CVs are among one of the most common X-ray sources in globular clusters. So they are usually signified by, characterized by strong UV and soft X-ray emission from the white dwarf and optical emission from the companion star. And sometimes they have very strong variabilities that can be observed in the X-ray and also in the optical sometimes. And another common source class is known as the chromospherically active binaries, or ABs. So these are actually close binary, but made of normal stars or sometimes slightly evolved stars. So, but the difference from these binaries to other ordinary binaries in globular clusters is that they are in very close orbits. So the stellar components in the binary is usually tightly locked to the orbit. So it's forced to rotate in a very fast rate of speed. The orbital period can range from less than a day to several tenths of a day, and that fast rotation of the star can induce high magnetic activity on the chromosphere, and that can emit X-ray in the observable level. So my research is basically, I got X-ray sources from Chandra observations, and I compile a list of X-ray sources, and then based on the list of X-ray sources, I have all the positions up and the Chandra localization of the X-ray sources, and then I try to incorporate other aspects of information such as counterpart searches, searches for counterparts in UV, optical, and radio bands, spectral properties like the shape of spectrum, or if there's any interesting line feature or absorption feature, and temporal analysis for variability and periodicity for some of the X-ray sources. That might be a very crucial aspect to identify the X-ray sources. And membership probability, of course, this is also very important to actually confirm if the X-ray sources is actually a member, not some chance alignment with the cluster in the direction of the globular cluster. So based on all this information, I classify the X-ray sources into the 4 major categories, and also excluding some non-members to the globular clusters. So And among all these specs, the most important part is of course to find counterparts in other wavelengths to so you can get more information from other wavelengths. But even with the X-ray localization provided by Chandra, what we usually do is to find optical counterpart, UV counterparts to the globular cluster X-ray sources. But even with the Chandra localization, because the very high stellar density in globular cluster, if you draw an error circle, the Chandra error circle, which is typically subarc second in size, you will still enclose several optical sources inside the error circle. So these are 95% error circles, 95% confidence circles derived from Chandra observations. And you see for each of the error circles, you can have multiple optical sources inside. So it's really hard to determine which one is the true counterpart, which one is not a counterpart, and what it is. So it's very important to also incorporate other information such as photometry of these stars to determine which one is the true counterpart. So I will just show you some examples in my research that I use to identify and classify different X-ray sources. For CVs, what we usually use is UV photometry and also VNI photometry. So in the UV bands, what we expect is that strong emissions are from the white dwarf and or the accretion disk around the white dwarfs. So what you usually see for CV counterparts is that they have blue excess. So here is a UV versus U versus UV minus U color magnitude diagram here. So basically bluer stars on the left and redder stars on the right. So CV counterpart usually have this strong UV excess or blue excess on the CMD, whereas on the V minus I color magnitude diagram, you're expecting most emission from the companion star. So you see typical CV like source C here is consistent with the mean sequence because you are seeing mostly emission from the companion star. So it's more likely to be consistent with the mean sequence. But CVs also have very strong variability in the optical and the UV. So sometimes you have the weird combination like source 9 that have a blue excess here on the UV CMD, but has a red excess on the V minus I CMD here. But that's not uncommon in globular cluster, I would say. It happens in several globular clusters, and it's certainly a very interesting case to follow up in the future if we get more time and spectroscopy probably or similar observations for these sources in the future. So these are very interesting cases to further study for sure. And also ABs can also be effectively classified by using UV and also sometimes V minus I photometries. So for ABs, because these are active binary, they are binaries in nature, so they are usually found to be consistent with the binary sequence of the color magnitude diagram. So which is slightly above the main sequence of the CMD. And sometimes you can have a slightly evolved companion or counterparts to these source classes, like A2 here, which is on the red giant branch. So those are known as the RSCVN type of ABs. And also W16 here is in a very unique, I would say very abnormal locus on the CMD because it's not predicted by single stellar evolution theory. So this position is known as the sub-subgiant branch star. And sub-subgiant branch stars are basically a locus below the subgiant branch, but rather than the main sequence. And it's not predicted by single stellar evolution theory, but has something to do with binary evolution. And in fact, a lot of sub-subgiant branch stars have been found to be associated with binary stars, and some of those are also X-ray. Some of those also have an X-ray counterpart to it. So they're definitely related to binaries, and also some of them probably related to interactions or mass transfer in the binaries. And for other sources, for sources beyond ABs and CVs, you probably need more information than just photometry and localizations. For example, in one of my study of the globular cluster M3, we found the second brightest X-ray source in this globular cluster has a very soft X-ray spectrum that can be fitted with a black body or a neutron star atmosphere model. So we think at this brightness and also with this soft X-ray spectrum, we think it might be a quiescent low mass X-ray binary containing a neutron star. So if you try with a VMICA, which is a thermal plasma model usually used for CVs and ABs, you will find a slightly worse fit to the spectrum. So we think it's better described by a neutron star atmosphere model, and we definitely propose for more time and observation for this. We have an accepted XMM observation for this globular cluster, and hopefully we can get more photons to to put more constraint on the neutron star radius and mass for this system in the future. And besides optical and X-ray, I also use observation from radio imaging survey, specifically the Maverick survey. So Maverick stands for the Milky Way Atacant VLA exploration for radio sources in clusters. It's basically a deep radio imaging survey of 50 globular clusters with the Australia Telescope Compact Array and the Carl G. Jansky Very Large Array. So Attica is for more of the southern cluster, whereas VLA is for more of the northern clusters. The dedication for the project is to find more accreting compact objects, especially accreting stellar mass black holes and some metal-sun pulsars, and probably some CVs and ABs are also radio emitters, but we haven't found any radio emitting CVs or ABs in globular clusters. So mostly stellar mass black hole and metal-sun pulsars. The collaboration spans from for several different institutes, MSU and Texas Tech, and Observatoire de Paris, and International Center for Radio Astronomy Research, and also U of A. If you're interested in the survey, there's a published catalog paper, I think published last year by Shishkovsky et al., 2020. So that has the VLA part of the survey catalog compiled in the paper, and I think there are more than 1,000 or probably 200, probably 1,200 sources discovered in the VLA part of the survey. So if you're interested, you can definitely go and check the catalog paper. So here I was just mention one of my research with the Maverick survey. So we discovered a likely, well, I would say a pretty confident metal-sun pulsar candidate in the globular cluster 6397. So U18 is the name of the X-ray source right here. This source was previously suggested to be another metal-sun pulsar in the globular cluster. There's a known metal-sun pulsar called U12. I don't remember where it is, but it's somewhere in the core. And we cross-match the X-ray position or overlay the X-ray position on the radio image. And we find the radio source here is actually position coincide with the X-ray source. And the radio source, U18, is very steep. That's typically a feature of a metal-sun pulsar or radio pulsar. The spectral index is -2.0. So alpha is defined in this formula here. And as I said, it was previously suggested as another metal-sun pulsar because it's so similar in terms of photometry, optical photometric property, and also X-ray variability, and also now with the radio steepness of spectrum, it's very similar to another known pulsar in the same globular cluster. So I think it's another metal-sun pulsar in the same globular cluster, and but was not detected by previous Parkes timing searches. Partly because we think that a U18 is probably one of those hidden pulsar that is continuously obscured by shocked material at the collision between the companion star and the neutron star. So pulses from the pulsar might have been smeared out or scattered. So it's not detected by timing searches in the previous studies. But now a recent studies on the optical using a series of Hubble Space Telescope observation of U18 suggests a 2-day orbital period for the system. And also, I think just pretty recent, probably a couple of weeks ago, there's another pulse signal confirmed by Parkes search, although the timing solution is not done yet. But I think the preliminary result is that the orbital period confirmed by Parkes is consistent with that we confirmed with Hubble Space Telescope HST observation. So that's a pretty promising target of meson pulsar in this globular cluster. And moreover, uh, this also opens a new window to find more systems like U18 globular clusters. So there are probably even more hidden meson pulsars, as observed by the Maverick survey. So that's actually another ongoing project I'm working on right now. So here's is a summary of all the VLE sources as observed, all the VLE sources as observed by the Maverick survey. So that's the low frequency band flux density versus the alpha spectral index. So the shaded area here is the typical spectral index range for known pulsars. And if you just plot this range and you just apply this spectral index range for the pulsars, you will still have a lot of candidate pulsars. So we're especially interested in the candidate that have either a Chandra or an optical counterpart. So you have more information, so you can get more information of the radio source, and just to follow up with further study, further observations, or to study its X-ray spectrum or something like that. So there are currently a total of 25 pulsar candidates that has a Chandra and or optical counterparts in I think a total of 15 globular clusters. And there are also some known pulsar detected by Maverick, as shown in the orange markers here. And lastly, I want to mention my ongoing recent project I'm working on right now, which is already submitted to AppJ actually. But it's also a use of the Maverick catalog to study the possible origin of globular cluster radio sources. This is so similar study have been done for X-ray sources in globular clusters. It's basically an investigation of what makes the X-ray source population in different globular clusters, and just try to see if there's a correlation between the number of X-ray sources versus the structural and dynamical parameters of the globular cluster. So we use a simplified model that the number of radio sources in the core is linearly correlated with the encounter rate, which is gamma, and the total mass of the globular cluster. And then we fit the model to our data using a maximum likelihood method. And so here's the result. So this is plotting the distribution of deviation from the maximum likelihood, which correspond to the best fit. So the best fit is at the zero, at where the deviation is zero, which is right here. We also have confidence contours plotted in the parameter space. So as you can see, non-correlation, which correspond to A equals B equals 0, is excluded at 99% confidence. So that means there's at least some dependence on either gamma or the total mass of the globular cluster, or both. So we know that member radio sources in globular cluster could be meson pulsar and mostly black hole low mass spectral binaries. So meson pulsars have been studied intensively in the past, that the meson pulsar population is correlated with gamma, the encounter rate. But black hole low mass spectral binaries might have a more complicated dependence on the structural and the dynamical parameters of globular clusters. So it's not it is not exclusively depend on the gamma or exclusively on mass. As you see, the B equals 0 here is excluded at 90% confidence, right? So it's not exclusively gamma for sure, at 90% confidence. I would say it's for sure, but yeah, it's very interesting study to get more time and to get more investigation to the study, and to hopefully we can put more constraint and tighter constraint on the parameter space in the future study if we get more member radio sources identified as black hole low mass spectral binaries or meson pulsars. So finally, some takeaways. X-ray sources in globular cluster can be created by dynamical encounters, and we can use UV and optical photometry to classify some of the X-ray sources effectively, such as ABs and CVs. And we can also use deep radio imaging surveys to review some of the X-ray sources, to identify some of the X-ray sources, such as meson pulsars or black hole low mass spectral binaries, which will for sure lead to more discovery of this kind of objects in the future with deeper observations, and also like higher sensitivity of the instruments. And globular cluster radio sources, as I showed in the last slides, the number of radio sources are correlated with the encounter rate and or the globular cluster masses. So that's pretty much my talk. I'm open to questions. Thank you.
All right. Excuse me. Thank you, Cory, for a great talk. Do we have any questions? You can raise your hand or put your question in the chat. I'll give people a few seconds. I guess you can also just speak up. I know sometimes people have trouble using the raise hand feature. Well, I am not seeing any questions. So I will give it a couple more seconds, but we are past the half hour, so I guess we should move on. All right, I don't see any questions. Feel free to contact Cory if you want to discuss further. And Peter, on to you. Thank you again, Cory.
Thank you.
All right, I'd like to introduce our next speaker, Elisa Costantini. She obtained her PhD in 2004 at the Max Planck Institute for Extraterrestrial Physics. She did a postdoc at the University of Utrecht. And since 2008, she's been a staff member at SRAN, the Netherlands Institute for Space Research. She is co-chair of the Athena Working Group of the ISM and co-chair of the AGN Working Group for ARCUS. She is PI of the Swiss-Dutch hardware contribution of the Japanese mission XRISM. And her scientific interests include the study of the ISM in X-rays, as well as winds in AGN and X-ray binaries. Please take it away.
Thank you. Give me 1 second. I'm going to share my screen. Share. Play from start. Here we go. I hope you see my screen now.
Yes, well, yes.
Confirmed? Okay. So if you are all hearing me and seeing my screen, I go on. Thanks a lot for inviting me. So now I will talk about interstellar dust as seen from the X-ray perspective. So the work that I'm going to present has been done with the collaboration with the precious collaborations of the people listed here in this slide. Okay, so for people who don't work with interstellar dust every day, this is a very simplified cartoon that explains how dust is actually formed. So dust is present in every stage of the stellar cycle. Let's start from the molecular cloud where everything begins. The molecular cloud is formed by gas, by vast majority, but also by dust. Then parts of it collapse and forms stars. So then everything that is around the star forms the circumstellar disk and eventually the planets that form any star system, and also rocky planets like our own Earth. As the star evolves along the HR, in the HR plot, the star becomes a red giant, and as we know, a large part of the outer envelopes of this red giant is given back to the ISM under the form of a stellar wind. So as the temperature decreases as you go farther away from the giant, the gas coagulates again into dust. Of course, depending on the size of the initial mass of the star, you can also transform this red giant in a supernova, and then all the elements that are beyond the iron, say the iron group, are also restituted to the ISM and eventually coagulate into dust. So while in the supernova event, you create basically heavy elements, elements that are have an atomic number larger than iron, at the red giant stage, you produce all the lighter elements like oxygen, silicon, magnesium, and other elements, and carbon, of course. And then, you start the cycle again. Of course, if you are so lucky of having at some point a neutron star merger, then you will also create all the other elements in the periodic table that are also coagulated into solid grains. So Carl Sagan said that we are made of stardust, and so this cartoon proves that is right. Right now, people think that stars are not only are not the only place where you can form dust, but also other privileged places in the ISM should be cradle of dust formation, like molecular clouds, for example. So if you study interstellar dust, for example, at longer wavelengths, people understood a great deal of interstellar dust. So in terms of chemistry, dust is formed by carbon in the form of graphite or polycyclic aromatic hydrocarbons that are a middle way between being a molecule and a dust grain, and silicates that are compounds formed by magnesium, silicon, oxygen, and iron, with small inclusions of also calcium or aluminum, for example. The dust sizes ranges from 1 nanometer to approximately 0.5 microns. And these sizes distribute in a simple way as a power law, where A in this equation, in this relation, is the dust radius. So this is a very simple way of parameterizing the dust size distribution. So the ISM dust grains are born in crystals in the winds of AGB stars. But then the harsh conditions of the ISM, like UV radiation, for example, makes it glassify the dust. So the nice order in the lattice is lost. And then you get amorphous dust. So this dust is often approximated as a sphere, but is irregularly shaped, often elongated, and often porous. So I don't have to explain to this audience the importance of X-rays, of course, but so let me remind you why X-rays are important for the study of interstellar dust and interstellar matter in general. Because thanks to the large energy coverage, we can study all the features that belong to the gas phase, for example, nitrogen, oxygen, iron, neon, magnesium, and silicon. And luckily, many of these elements are actually included into dust. So in the X-ray band, we have direct access to the features of oxygen, iron, magnesium, and silicon, all located in the soft X-ray band, except for the iron K. And these are constituents of the silicates, the main constituents of silicates. So studying dust in the X-ray band actually means studying the silicate content of the ISM. And also there is another advantage in the X-rays. So there are prominent iron features that are well isolated. We have the iron L edges and the K edges. So in the infrared band and at other wavelengths, there is no distinctive feature of iron. So X-rays gives you a window on the iron content of the ISM. So from what I said is straightforward to understand that we can measure how much a certain element is depleted into dust, as we have access to both the gas phase in the X-ray band and the interstellar and the solid phase. So we measure both, and we can understand the ratio. So X-rays are also sensitive to a large range of column densities, and X-ray binaries that are so bright are used as background light. So we can map all the galactic plane. Okay, so this is of course trivial for X-ray experts, but one of the way of observing dust is through absorption. Another way is from studying the scattering halos, but unfortunately I don't have the time to go into it today. So we have our X-ray binary in the background and our clouds that are intervening along the line of sight, and we observe it. So here on the right-hand side, we see a detail of the silicon edge as observed by Chandra. And you see that the silicon edge is definitely not a simple feature. It's full of details, and all these details are actually a signature of dust. So you see that these features are actually detectable by current instruments. But so why is that we have these extra features in an absorption spectrum? So the reason is actually very simple. So we have an incoming X-ray that penetrates a solid. So the electron wave that is generated will just oscillate, and will interact with all the other neighboring electron waves that are in the solid. So in a solid, we have electrons that are highly packed together, unlike the gas phase. So this will generate constructive and destructive interference. And this will have an effect on the absorption cross-section. So you see that many extra features will be present, and these features are like one or two electron volt wide. And depending on the chemistry of the grain, these features will be different. So you see immediately that if we go to an astronomical spectrum and try to study it, in principle, we can understand the chemistry of the interstellar dust. Okay, but this is not very simple, because it is all very well to study high resolution X-ray spectra, for example, with Chandra. But if we don't have a complete set of models that are reliable, it is impossible to model these features. So up to a few years ago, indeed, the information was very sparse, because none of the elements that were interesting for astronomy were ever observed in a systematic way. So what we did was a campaign taking approximately 20 samples, including silicates with different magnesium to iron ratio, oxides, sulfates, and observe systematically all edges that they would produce using synchrotron facilities all over Europe, and also an electron microscope in Spain. So this was a really big endeavor. But then, we have now a model that we plan to implement in fitting programs, and of course, everything that has been published is already public. All the data, all the cross sections are already public. And so here is an artistic impression on how it would look like. So on the y-axis, you see transmission as a function of the energies in the X-ray band. And these are all the edges we dealt with. So of course, this work is never ending. So we are still making additional measurements, for example, on sulfur and on carbon and calcium as well. Okay, so let me go on. And so for today, we can only focus on one edge and what it means. So we focus on the silicon edge, the silicon K edge that is at around 6.7 angstrom, which is 1.84 keV approximately. So here in this plot, we see like an example of our measurements. On the y-axis, you see a measure of the cross-section, of the absorption cross-section, and as a function of wavelength. And this is the silicon edge. So you see immediately that when we zoom in into this region where the secondary peaks are, we see that these samples actually differ significantly. So there is really a variety of features, and the majority of them can be easily measured in an X-ray spectrum. Okay, so let me remind you how it was done, in the old days. So here is the silicon edge as we have seen before, and this was the old way of fitting it, just taking a photoelectric edge as caused by gas phase, and fit, this step function. So you see that all the details were absolutely missed, and so we missed a lot of information about dust. So what happens when we use our models? So this is again a silicon edge, and this is on the y-axis, as you see, transmission as a function of wavelength again. So the blue line is gas again, and is relegated where it belongs. So it's a very small contribution to the absorption, which is also in agreement with what with the studies at other wavelengths that says that silicon should be 80–90% depleted in the interstellar method. So the vast majority of absorption is made by dust. That nicely fits all the pre-edge feature and also the post-edge features. So in this particular case, the best fit was provided by a mixture of olivine and crystal, olivine amorphous and in crystalline form. So let me go a little bit in detail on what you can learn about this type of analysis. So first of all, let's go to the absorption features. So here, not only you can understand the chemistry of the interstellar, the intervening interstellar dust, but also you can guess if the dust in front of you is crystalline or amorphous or a mixture of the two. So let me remind you that in a crystalline configuration, the lattice is very well ordered, and it produces very sharp features, especially in the silicon edge. While when the dust is glassy, then this nice ordered configuration is completely lost, and then this results in smoother peaks. Okay, so then the post edge, as you can see, is a diagnostic for the chemistry and the crystallinity of dust. But not only, there is a pre-edge. The pre-edge is actually a scattering peak, because of course we don't have only absorption along the line of sight, but we have also scattering. Together they make the total extinction along the line of sight. So this peak arises due to scattering and depends mainly on the particle size of the dust grain. So again, we have a new diagnostic about the size of the dust grains. Because, for example, if you compute the same transmission with two different dust size distributions, you see that this peak, the pre-edge peak, increases if you increase your dust size. So here is a comparison between a classical distribution in the red line and something that is more skewed towards large grains. So if you actually include large grains, you are, this could be a possibility of fitting, of better fitting the pre-edge in this particular source. Okay, so this is with Chandra and XMM. We did many studies of about the intervening interstellar dust. But of course, with future instruments, we will be able to really open up like new new occasions of studying interstellar dust and doing new things. So here on the left-hand side, you have an effective area plot that I'm sure you're all familiar with. So at the bottom, we have the usual suspects, so XMM and Chandra. And we see that we will increase the effective area, especially above 2 keV, with Chrism and Athena. And on the other side, if hopefully Arcus will be accepted, we will explore all the softer energy range. Yeah, I heard the beeping. Okay, on the right hand side, on the other hand, we see the resolving power. We see RGS, Meg, and Heg specialized in the soft energy range, while Chrism and Athena will provide a 5 electron volt resolution and a 2.5 electron volt resolution at energies above 2 keV. So Arcus will have also a constant resolving power at about 3,000 in the energy range below 1 keV. So let me illustrate you what we can observe. So this is a summary plot of this concept, but you should only look at the top panel, where the diamonds tells us the elements that can be studied with current instruments. So here is elements as a function of energy, and this is on the y-axis we have abundance. And in triangles indicate the elements that will be able to study with future instruments. So here we have carbon on the left-hand side, studied by Arcus, and all the rest by Chrism and Athena. Okay, so let me show you some simulations. So what does it mean physically that with Chrism and Athena will be able to access the region above 2 keV? So it means that we can access regions that are very dense, with column density that are up to 1 in 10 to the 23 centimeters to the -2. So the densest regions of our galaxy, where the optical extinction is about 50, so only the X-rays can really penetrate these regions and study, for example, the iron K edge. So iron content again in the ISM. So here is a simulation on the left-hand side of the iron K edge for different models. And you see that the data will be able to discriminate easily among different models. And if you remember the silicon edge that I just showed you, and here is a simulation of Athena, you see that the silicon edge, understanding the silicon edge secrets, the chemistry, the crystallinity, and the dust size distribution will be a matter of seconds, actually of 10 kiloseconds. So Athena will open, but also Chrism before that will really open a new page of interstellar dust studies. So let me show you two more simulations. On the right-hand side, we have the Sulfur K Edge. So sulfur is a very controversial element because people think that either is not included at all in the interstellar dust, in the diffuse interstellar dust, or it is depleted a little bit. So here you can see that Athena will be able also to understand if sulfur is depleted only a little bit. And Athena, but also Chrism, will be able to evaluate a jump of only few percent in the spectrum. Here is shown in the transmission y-axis. And here on the left-hand side, we have a simulation of the carbon K edge that Arcus will observe at best. And finally, we will be able to understand the nature of carbon that has been debated for many years now, if carbon is in the form of graphite, of amorphous carbon, or even hydrogenated amorphous carbon. So we are really looking forward for these missions. to these missions. So conclusions. So high resolution X-ray spectroscopy plus reliable laboratory measurements really led to an incredible leap forward in our understanding of interstellar dust. And then future instruments like Prisma, Athena, and Arcus will explore for the first time the densest region of our galaxy, but also, the very soft regions of the X-ray spectrum. So thanks very much.
All right. Thank you, Elisa, for a great talk. We have time for questions. If you want to use the raise hand function in the use the reactions button, or we can read off questions that are typed into the chat window. We have a question from RKS.
That would be Randall.
Oh,
Hi,
hey.
Elisa.
Hi.
Thanks for the thanks for the shout out to all three of my favorite missions. So, what are your plans for the future? What is the next set of observations for laboratory experiments that you're going to be running?
Okay, so of course everything was a little bit blocked because we couldn't go anywhere for the last year, but we have in line carbon measurements, and we are measuring other sulfur and calcium bearing compounds, not in Europe this time, but in Taiwan. So this is the short term. The short-term plan.
Thanks.
All right, we have time for more questions. Okay, there's a raised hand for Steve Wilner.
Hi, I'm an infrared guy, so familiar with dust, but not for this angle of it. Thanks very much. This is fantastic stuff. You showed at the end some of the simulations, but I'm wondering if you could give an overall assessment of distinguishing between gas phase and solid phase. Where are we likely to be on that in 10 years or something?
Okay, so I understood the first part is like, so you asked me how we can distinguish the gas phase from the solid phase in the X-rays?
Well, the simulations showed the idea, so
yes.
I get that. But I'm curious with practical signal to noise and practical observations,
Okay.
where are we likely to be ending up in that?
Okay,
kind of summarize.
Well, the good news is that we can distinguish between gas and dust also with Chandra or XMM. And the reason is simple, in the sense that all the dust features show up in the post-edge environment, while the transitions that belong to the ISM, for example, I don't know, the main features of oxygen or so, they all show in the pre-edge. So they are very, very well distinguished. And so this is a distinction that we can do also now, quite easily, actually. And the other thing that makes it easy is that all these features are actually linked. Say that you see features from oxygen and then iron, and so you don't go fitting one single feature at a time, but we use synthetic models. So every phase has a temperature. So then line ratios are fixed. So then this helps a lot in reducing uncertainties. And in the future, of course, it will be even better.
All right. We might have time for one more question. If not, then let's thank both of our speakers for a couple of great talks. And thank you all for coming to join us.
Thank you, everyone.
Bye-bye.